Okay, so let's review what we did last Tuesday. So we studied there are 5 phase change processes. The first one is compressed liquid. Saturated liquid, saturated mixture, saturated vapor, and superheated vapor. So whenever we have a phase change material, to evaluate its property, we need to determine the phase change process. So to determine this phase change process, we can use property diagram. There are 2 property diagrams. The first one is PV diagram. PV diagram shows how temperature and specific volume are related at a given temperature, at a given pressure. So if you know the pressure of your system, you can make PV diagram, and this PV diagram looks like this. To complete this PV diagram, you need to know 3 reference properties. They are T set, the saturation temperature at this pressure, Vf, the specific volume of saturated liquid. So this one is specific. So F means specific liquid. And Vg, the specific volume of saturated vapor. Then on this PV diagram, here is number 1. This point is number 2, saturated liquid. This is number 3, saturated mixture. This point is number 4, saturated vapor and superheated vapor. So that's how you make this PV diagram at the given pressure. There is another property diagram that you can make. This PV diagram, you can make this PV diagram at this pressure. So assuming that you know the pressure of your system. If you do not know the pressure of your system, but you know the temperature of your system, you can make another property diagram. So let's say the temperature of your system is 30 degrees Celsius. You can make, instead of TV, you can make PV diagram. This PV diagram looks similar to this PV diagram, however, upside down. So PV diagram looks like this. And there are 3 properties you need to complete this PV diagram. They are T set, Vf, and Vg. Here we have compressed liquid. This point is saturated liquid, saturated mixture, saturated vapor, and superheated vapor. At this temperature. So if you know pressure of your system, you can make PV diagram. If you know temperature of your system, you can make PV diagram. Once you make PV or PV diagram, you can find, the where your system equals to S. That's how you determine the phase change process of your system. So this is the step number one whenever you want to evaluate a property of a phase change material. Okay. Then, what is this T set? T set is the saturation temperature, which is the boiling temperature of your system. So, at this pressure, if you increase the temperature of compressed liquid, then the temperature reaches the saturation temperature, which is the boiling temperature. And then, the boiling starts, which is saturated liquid, saturated mixture, and saturated vapor. So these are phase change from number 2 to number 4. And then, once the phase change completes, then temperature goes up, which is superheated vapor at this constant pressure. You can also, make phase change instead of increasing temperature, but decreasing pressure. So at this constant temperature, if your water is at compressed liquid, you can decrease the pressure of your system. Then once it reaches saturation pressure, then phase change occurs. So you can see liquid molecules become vapor molecules. Then there is a phase change from liquid to vapor, and once it completes, it is a saturated vapor. And if you continue to decrease the pressure of the system, then it becomes superheated vapor. So that's how phase change occurs at a constant pressure, at a constant temperature. Okay? So it is very important for you to understand how to make this PV and PV diagram. So let's look at this PV diagram. If your phase change material has different pressure, different than this 100 kilopascal, let's say 200 kilopascal, then where is the PV diagram is going to be? So if you increase the pressure, let's say 200 kilopascal, then PV diagram moves upward. So this is the PV diagram at 200 kilopascal. If you decrease the pressure of your system, let's say 50 kilopascal, then PV diagram is going to move downward. And here is PV diagram for 50 kilopascal. Then this point is saturated liquid. This point is saturated vapor at 200 kilopascal. This point is saturated liquid, and here is a saturated vapor for 50 kilopascal. If you connect all the saturated liquids and saturated vapor, they will meet at a point, at some point, which is called critical point. So above this critical point, there is no water, but supercritical fluid. Similarly, on this PV diagram, if you increase the temperature, let's say, the 50 degrees Celsius, then this PV diagram moves upward. So this one is 50 degrees Celsius. If you decrease the temperature, then it moves downward. So that is for 10 degrees Celsius. Again, you can also make this curve And the name of this curve is saturation curve. This one is saturation curve. The same thing here. Okay. One last thing, before we move on. So if you use this PV diagram, you can determine specific volume. If you use this PV diagram, you can determine specific volume. What about, what if you want to determine a property other than this specific volume? Let's say instead of specific volume, I want to determine the specific internal energy or specific enthalpy. By the way, we don't know what is enthalpy now, but we are going to study this one today. Then there's a very simple way to evaluate U and H. On this TV diagram, this horizontal axis is specific volume V. You can replace this specific volume V with U. So instead of VF, you can say UF, UG. That is, so this axis is going to be specific internal energy U. Or you can also say H. Instead of UF, you can say HF, HG, and the horizontal axis is going to be H. Similarly, on this PV diagram, instead of PV diagram, you can make TU diagram. Then this one is going to be UF, UG. Or if you want to determine this H, you can make pH diagram. Then it's going to be HF and HG. Okay. So that's how you can make PV, TU, TH, PV, TU, TH. Okay. These property diagrams are very important. You need to make sure that you can make those TV and PV diagrams. This is the very beginning of any thermodynamic analysis. So if you are not able to make these TV or PV diagrams, you cannot solve any problems afterward. So this is very important. Okay. We have a number of practice problems on this PowerPoint slides later, so we are going to practice how to make these property diagrams and how to evaluate the property. So don't worry about that for now, okay? So just to make sure that you memorize how to make these property diagrams, okay? So let's talk about T set and P set. Saturation temperature and saturation pressure. This saturation temperature is the temperature when a system undergoes phase change at a given pressure. This P set is saturation pressure, the pressure, when a system undergoes a phase change at a given temperature. Is P set and T set, they are functions of, so for example, this one is T set. So this T set is a function of pressure. So at 1 atmospheric pressure, T set is 100 degrees Celsius. So this is the boiling point that we know. The pressure in this classroom is approximately 101.325 kilopascal. So if you boil water, the temperature is going to be 100 degrees Celsius. But if you go to, let's say, Denver, Colorado, atmospheric pressure is only 80 kilopascal, then the temperature, the saturation temperature is only 93.3 degrees Celsius. What about, on top of Mountain Everest? It's about 8 6,845 meters, so which is right below this one. And the atmospheric pressure is going to be around 30 kilopascal, and the boiling temperature is going to be approximately 70 degrees Celsius. So when pressure goes down, then the saturation temperature goes down. If you increase the atmospheric pressure, the saturation temperature goes up. So if you buy a pressure cooker at a Target or something, if you cook, something, the boiling temperature inside the pressure cooker is going to be greater than 100 degrees Celsius because the pressure inside is going to be higher than atmospheric pressure. On the other hand, this table shows saturation pressure, P sat. This is the pressure when a system undergoes phase change. So you can increase the temperature to have a phase change, or you can decrease pressure to have a phase change. So what is the temperature in this classroom? Approximately 20 degrees Celsius. It's the room temperature. Then the saturation pressure is 2.34. What is the atmospheric pressure in this classroom? 1 atm is 101.325 kilopascal. That is the pressure in this classroom. If you decrease the pressure in this classroom from 101.325 down to 2.34, you will see water is going to undergo a phase change. Okay? So these are some background, the information you need to know to be able to make these diagrams. Then let's see, how we can use these TV diagrams to determine the phase change process. So let's do an example. So let's assume that we have water and I was able to measure its pressure. So the pressure was 100 kilopascal. And the temperature was 200 degrees Celsius. What is the phase change process of this water? Pretty easy to understand because 100 kilopascal is similar to the atmospheric pressure in this classroom. So we know water boils at 100 degrees Celsius. So if it is 200 degrees Celsius, it's going to be vapor, right? So that's how we understand from our experience. In thermodynamics, we can make TV diagram to determine the phase change process of this water. So let's do that. We can make either TV or PV diagrams. In this case, we know pressure and temperature, both of them, so we can make either of them. So which one? So I'm going to use this 100 kilopascal to make a property diagram. So I'm going to say at 100 kilopascal. So if you know pressure, what kind of property diagram can you make? If you go, yeah. So if you know pressure, you can make temperature diagram. If you know temperature, you can make pressure diagram. So if you know pressure, you can make temperature diagram, which is TV diagram, temperature specific volume, not the TV when we say television, right? So this TV diagram looks like this. So let me make this TV diagram. To make this TV diagram, we need to know three properties: P sat, VF, VG. So here we have T set VF VG. Then where can you find T set VF VG? What information do we know for this diagram? The pressure, 100 kilopascal. So you can go to the pressure table, which is table A3. So here is the pressure table. Properties of saturated water pressure table, table A3. So let me explain how to read this table. The first column is the input. So if you know pressure, any properties next to it is going to be, the properties you can use. So what is the pressure in our system? 100 kilopascal. What is the unit of this pressure? Bar. 1 bar is 100 kilopascal. So we want to, to find 1 bar here. So any value at 1 bar, these values are what we can use. Okay? So what do we need to complete this TV diagram? We need to know T set. T set is the second column. So what is the value? 99.63. So I'm going to write T set is 99.63 degrees Celsius. Then what is VF? VF is here, this VF. However, the specific volume of saturated liquid, which is VF, is very small. So we multiply this value by 1,000 and wrote them here. So the actual VF is going to be this value divided by 1,000. Okay, so 1.0432. 1.0432 times 10 to minus 3. So that is the specific volume of saturated liquid. What is the unit? The unit is here, cubic meters per kilogram. Cubic meters per kilogram. What about VG? So on this line, VG is here, specific volume of saturated vapor. So we are looking at this value, 1.694. So 1.694 cubic meters per kilogram. So that's how you make TV diagram. Once you make TV diagram, we need to, to see where is compressed liquid, saturated liquid, those 5 phase change processes. You can see the numbers here, 1, 2, 3, 4, 5. So I'm going to write, this line represents number 1, compressed liquid. This point represents number 2, saturated liquid. This line represents number 3, saturated mixture. This point represents number 4, saturated vapor. And this line represents number 5, superheated vapor. So if you know pressure, you can make TV diagram. Once you make TV diagram, now it's time to evaluate the phase change process. How we can do that? So our assumption is that when pressure is this value, water should be on this line. That is our assumption, okay? Cannot be here, cannot be here. If water is here, that means that the pressure is greater than this value. When water is down here, the pressure should be less than this value. So when the pressure of the water is 100 kilopascal, that means somewhere on this line. So now, how we can locate our system on this line? We have 2 property values available. So we use the first one to make this property diagram. It's time to look at the other property that we know. What is the other property? Temperature. Temperature is 200 degrees Celsius. So where is temperature on this TV diagram? this vertical axis is temperature. So let's find 200. How can we locate our system? Oh, we know this reference value. T set is 99. So 200 should be greater than 99, somewhere up here. So where is our system? Number 5, superheat vapor. So that's how you evaluate the phase change process of your system. So you make this 100, you use this 100 kilopascal to create this TV diagram, then use the other property to locate your system. So 200 should be up here. So the only possible phase change process at this temperature is number 5. So you can say it is phase change process number 5, superheated vapor. That's how you determine the phase change process. But this one was easy because it is pretty easy to understand. The 100 kilopascal is the atmospheric pressure here. So we know the water boils at lower than this temperature. So we can guess that this one should be vapor. Then let's, ask another question. What about, we have a water and the pressure is 1.5, 150 degrees Celsius. So I measure the pressure. It was 150 kilopascal, and I don't know the pressure, but I have the specific volume. When I measure the mass and the volume of a system, it was 1 cubic meters per kilogram. Now, can you evaluate? Can you determine the phase change process? Now we have no idea, right? So this time we are going to use TV diagram, okay? So we are going to use the first property that we know, 150 kilopascal. So let's make a property diagram. If we know pressure, what kind of diagram can we use? There are 2 of them, temperature and pressure. If you know pressure, it's going to be temperature. If you know temperature, it's going to be pressure. So since we know pressure, it's going to be TV diagram. TV diagram. At what pressure? 150 kilopascal. And TV diagram looks like this. To complete this TV diagram, we need to find 3 properties. They are T set, Vf, and Vg. Where can you find T set, Vf, and Vg? From this pressure. So we can go to table A3, saturated water pressure table, this one here, and find 150 kilopascal. If you look at the unit of this pressure, it is bar. 1 bar is 100 kilopascal. So 150 kilopascal is 1.5 bar. So where is 1.5? Here. So 1.5 bar is here. So this one is T set, this one, and Vf is this number, and Vg is this number. So let me write these 3. By the way, be careful. This number is after multiplying Vf by 1,000. So Vf should be this one divided by 1,000. So let me write these values. First, T set is 111.4. 111.4 degrees Celsius. What about Vf? 1.0528 times 10 to minus 3 cubic meters per kilogram. What about Vg? 1.159. 1.159 cubic meters per kilogram. Then on this TV diagram, here you can see 1, 2, 3, 4, 5. Similarly here, 1, this point, 2, 3, and 4, and 5. So we are ready to determine the phase change process. Now, we made this TV diagram at this pressure. So it's time to look at the other property that we know. What is the other property? 1 cubic meters per kilogram. This is a specific volume. Where is the specific volume on this TV diagram? This horizontal axis is specific volume. So let's find 1 cubic meters per kilogram. Let's look at this VF. It's going to be 0.0010528. It's too small. So this specific volume is greater than VF. What about VG? 1.159. So this number is less than here. So our system is going to be, the specific volume of our system is between VF and VG. Somewhere in the middle. So what is the phase change process? Number 3. So you can say phase change process number 3, saturated mixture. What does it mean? The water is currently boiling, undergoing phase change between liquid and vapor. So you have a mixture. That's how you evaluate the phase change process of your system, by using a property diagram. So let's do one more example. And this time, we used PV diagram twice. So let's use PV diagram. That means we have water and we do not know the pressure, but we know its temperature. So I'm going to say we have a water again. And I know the temperature. Um, 50 degrees Celsius. So that is the temperature of the system. Let's find something, a new property. I know the specific internal energy, U, which is 100 kilojoule per kilogram. So if you have a water, when you measure the temperature, 50 degrees Celsius, when you measure the specific internal energy, was 100 kilojoule per kilogram. What is the phase change process? To evaluate the phase change process of this water at this condition, you need to make a property diagram, but not TV diagram anymore, because if you want to make TV diagram, what you need to know? Pressure. But this time we don't know pressure, we only know temperature. So if you know temperature, we can make, if you know temperature, we can make PV or PU or pH diagram. So let's do that. I'm going to make PV diagram again. Now we know U, so it will be convenient to make PU diagram. So let's do that. This time I'm going to make PU diagram. PU diagram looks like this one, going down, straight down. So PU diagram looks like this. And to complete this PU diagrams, to complete this PU diagram, we need to know 3 properties. They are T set, U at, UG. Just to remind you, this is extremely important in thermodynamics. You need to be able to evaluate the phase change process. Otherwise, you cannot solve any problem afterward. So this is very important. It's like, the plus minus in mathematics. If you want to study mathematics, you need to, you need to know how to add up, how to subtract, right? It's like that in thermodynamics. So where can we find P set UF UG from this temperature? So we can go to a property table, saturated water temperature table. That is table A2. Here. Table A2, properties of saturated water temperature table. And what is the temperature? 50. So let's find 50. The last one is 45. So we can go to the next page. Now there is a 50 degrees Celsius. So at this pressure, what kind of properties that we can use? Any property on this row, we can use them. So what do we need to first? What do we need? T set, saturation pressure. Where is it? Saturation pressure is here, 0.1235. But remember, the pressure on this table is in bar. So you need to convert this bar into kilopascal. 1 bar is 100 kilopascal. So 0.1235 bar is 12.35 bar. 12.35 bar. I'm sorry, kilopascal. What about UF and UG? UF is here, UG is here. So at this temperature, this is UF, this is UG. So there's a UF, UG. So let me write these values. 209.32. 209.32 kilojoule per kilogram. UG. 2443.5 kilojoule per kilogram. That's how you can make this PU diagram. On this PU diagram, the phase change processes are 1, 2, 3, 4, 5. Similarly, here, 1, this point, 2, 3, this point, 4, and 5. So now we are ready to determine the phase change process. We used this property, temperature, to make this PU diagram. Now it's time to use the other property to locate your system. What do we know? We know specific internal energy U. So where is U on this PU diagram? This horizontal axis. So let's find 100. UF is 209. UG is 2400. So 100 should be somewhere on the left-hand side. So I'm going to say, here is 100, this one. So what is the phase change process? Number 1, so you can say at this temperature and this specific internal energy, water should exist as phase change process number 1, compressed liquid. Any question about how to determine the phase change process? Very important. You need to completely understand. but I know it's first time, for you to use these graphs. So let's practice many problems together. Okay. Before we going forward, I told you that there are 3 properties that we can use for the horizontal axis. V, U, we know what is V, specific volume. We know what is U, specific internal energy. But H is new. So let's talk about H. H is called enthalpy. This enthalpy is a combination property. It has no meaning in thermodynamics. It means nothing in thermodynamics. However, it is just, the sum of U, specific internal energy, and PV, flow energy. It's just sum of these 2 energies. There is no other, thermodynamic meaning, but we use this H a lot because this U plus PV come together in many cases. And, we are going to learn, where we use this H later when we study a closed system and an open system. You see we use H more often than U or V, okay? But for now, we haven't studied closed systems and open systems yet. So let's just, accept it as is. So H is U plus PV, okay? And we can evaluate H in the same way we evaluate V and U, okay? Then let's go to the second step to evaluate a property. Again, let me review. The first step is always step number 1. Make a property diagram. So what they are, PV at a given pressure, or PV at a given temperature, or U or H. So now we know how to make them. Once you are able to make these property diagrams and determine the phase change process, now step number 2. It's time to use a table to evaluate their properties. From step number 1, you should be able to determine whether your system is number 1, compressed liquid, or number 2, saturated liquid, or number 3, saturated mixture, or number 4, saturated vapor, and number 5, super heated vapor. So we are going to use different tables for different phases. Okay, so we will study how to evaluate the properties of each phase change process. So let's go with the easiest ones first. There are 2 easy ones. Number 2 and number 4. If you have either a saturated liquid or a saturated vapor, finding their properties should be the easiest because their properties are already available on a table. So let's look at this one. If you want to determine specific volume, what is the first one? The specific volume of saturated liquid, VF. The property that we used to make a diagram. Or if you want to determine the specific volume of saturated vapor, here is VG. So If you have saturated liquid, which is F, if you want to determine specific volume V, it's going to be just Vf. Then you can find Vf directly here. If you know temperature or pressure, you can go to appropriate tables and determine Vf directly on this table. If you want to determine U, similarly, it's going to be UF. If you want to determine H, it's going to be HF. If you want to determine S, entropy, it's going to be SF. But we're not going to study this entropy until chapter 6. Okay? So finding the properties of saturated liquids and saturated vapors are pretty simple. But what about this vapor? Vapor is G. So if you want to determine specific volume V, it's going to be Vg. If it is U, it's going to be UG. If it is H, it's going to be HG. If your system is water, you can go to the water table, the water temperature table, or water pressure tables. They are table A2 and table A3. Table A2 or table A3. So those are the tables that you are going to use to evaluate these properties. If you know temperature, A2. If you know pressure, A3. Okay? What about if you have a mixture, saturated mixture, phase change process number 3. Saturated mixture means you have a saturated liquid and saturated vapor at the same time. So you have a liquid and vapor. But there are many different saturated mixtures. One mixture can contain 10% of liquid, 90% of vapor, or 50% of liquid and 50% of vapor, or 40% and 60%. So before you evaluate a property of this saturated mixture, you need to know what is the ratio between liquid and vapor in the mixture, right? So that ratio is called quality X. Quality X is the ratio between liquid and vapor. So if you own, so the mathematical form of this quality X is mass of vapor divided by mass of liquid plus mass of vapor. So if you only has liquid, then there's no vapor. So X is going to be 0. If you only have vapor, there is no liquid mass. So it's going to be mv over mv. So it's going to be 1. So this quality X should be between 0 and 1 to be a saturated mixture. If the quality X is 0, that means you have saturated liquid because you only have liquid. If the quality X is 1, it is saturated vapor. What about the quality X for compressed liquid? There is no quality X because the quality X is the ratio between saturated liquid and saturated vapor. If your system is away from a saturation, then there is no quality X. Okay? So there is no quality X for a compressed liquid or superheated vapor. Then once you know the ratio between liquid and vapor, then you can evaluate the properties of the mixture by linear interpolation. And if you don't remember how to determine, the mixture property by linear interpolation, but that's okay. Let me give you the equations. So if you want to determine specific volume V, the linear interpolation equation is going to be VF plus quality X times VG minus VF. So that's how you can determine the specific volume. What about if you want to determine specific internal energy U or H? You can use the same equation. Just replace V with U. U is UF plus quality X times UG minus UF. H is HF plus quality X times HG minus HF. S is the same equation, but let's study this as entropy later in chapter 6. So these are how to evaluate the properties of saturated mixture. That means you need to know VF, VG, UF, UG, HF, HG. So you are going to use table A2 or A3, depending on whether you know temperature or pressure. If you know temperature, always A2. If you know pressure, A3. So that's how you evaluate property of saturated liquid, saturated mixture, and saturated vapor. Then what's the next one? Superheated vapor. If you have a superheated vapor, we have a new table, not A2 or A3, A4. Oh, that's it. You can go to table A4. Let me show you an example. Table A4 looks slightly different from table A2 and 3 because it contains a lot of subtables for different pressures. So this table for 4 megapascal, this table for 6 megapascal, this table for 8 megapascal, this table for 10 megapascal. There are tables before this page. There are tables after this page. So you have a number of tables depending on the temperature and pressure. So pressure and temperatures. So if you know pressure and temperature, you can determine its property. But there's one problem here. So let's say that I have a water system whose pressure is this one, whose pressure is 4 megapascal, no problem, and whose temperature is 280, 320, and 360. I'm going to select 300. Oh, that's a problem. Now you know what is the problem. And now I want to determine its H. So do you know how to determine H? Oh, H is right here. So the H of my system should be somewhere on this column. So which one? 4 megapascal. We just need to find the temperature, 300. Oops, there is no 300. The 300 is greater than 280 and less than 320, so somewhere in the middle. So the H value is going to be between these two values. So how can you find H? Can we just say, oh, it should be between these two? That's the answer. No, you can't. You need to find the exact value. So how are we going to find, the H value at 300? You can use linear interpolation. Let me show you, how to do a linear interpolation. So it's going to be 300 between these two numbers. We want to determine H, so it's going to be between these two numbers. So we want to evaluate H at 300. So this is how you do a linear interpolation. There are many different ways. This is just one of them, but I found it is simpler than the others. So I recommend you use this one. So the left-hand side of this equation is going to be temperature, T. The right-hand side of this equation is going to be H. So in the denominator, we are going to write the lower bound and upper bound. So for this temperature, the lower bound is going to be 280, upper bound is 320. So 280, temperature is between 280 and 320. What about H? I'm going to write the H value corresponding to the temperature value at the same location. So on this left-hand side, bottom left, we have 280. On the right-hand side, bottom left, we are going to write H value at 280. So what is it? 2901.8. That is H value at 280. So at 280, 2901.8. What about the bottom right? Bottom right on the left-hand side, we have 320. So what is H at 320? H at 320, 3015.4. Now we want to determine the unknown H at 300. So H at 300. So where is 300? I'm going to write 300 here. Then where is the unknown H? So 300 is top left corner on the left-hand side. So top left corner on the right-hand side, we have the unknown H. If you solve this equation, you determine H. Oh, wait, we have this. We need to fill them by how? The number below. The number below. So this one goes up. You got promoted. So 320 goes up 3015.4. So if you solve this equation, you get H. That is H at 300 degrees Celsius. That's how you do linear interpolation. We have 15 minutes, so we can finish how to evaluate a property today. So today's lecture is one of the most important lectures in this course. So I will do my best to upload today's lecture recording as soon as possible, maybe tonight or tomorrow if you need to review it. Okay. So that's how you determine the phase change process of superheat vapor. But one is missing, compressed liquid. So if you have compressed liquid, how to evaluate its property? Then why do we study the compressed liquid at last? Because it's the easiest one? No, the other way. It's a little bit complicated, but not a lot, okay? So evaluating a property of compressed liquid depends on its pressure. Then let's see, why I'm saying that like that. If you go to superheat vapor table, you have 4 megapascal, 6 megapascal, 8 megapascal, 10 megapascal. What is the atmospheric pressure in this classroom? Only 0.1 megapascal. So do we have a 0.1 megapascal? Yes. There are a number of tables in this table A4, and you have a 0.06, which is about 6 kilopascal, 35, 70 kilopascal, 100 kilopascal here. So you have many tables for superheat vapor. Then, isn't there a table for compressed liquid? Yes. just this one page. We have a 2.5 megapascal, 5 megapascal, 7.5, 10 megapascal, 15,200. So one thing you can notice is that, oh, those pressures are pretty high. Then why there is no property table for compressed liquid at low temperature? Because at low temperature, there is minimum difference between saturated liquid and compressed liquid. So when pressure is low, how low? Less than the lowest pressure in this table, 2.5 megapascal. If the pressure is less than 2.5 megapascal, then our assumption is there is no difference between saturated liquid and compressed liquid as long as, so the pressure is constant, as long as temperatures are the same. So if you want to determine specific volume, it's going to be specific volume of saturated liquid at the same temperature. So I don't have a water bottle, but let's assume that this is water bottle, 20 degrees Celsius. Now, presently, compress the liquid. If you pressurize it, or if you, vacuumize it, it will change pressure. However, does it change the property of this water? If you pressurize it, you cannot drink anymore. If you depressurize it, you cannot drink anymore. No, you can drink because there is no significant difference in their property. But if you increase temperature, let's say from 20 degrees Celsius to 100 degrees Celsius, can you drink it? Yes, one time, because it's too hot, right? So if you change its temperature, its property dramatically changes. However, if you change pressure, not a lot, unless you can, the increase pressure like by 1,000 times, then it matters. But from 1 atm to 2 atm, 3 atm, no, it doesn't change. So as long as temperatures are the same, the pressure change doesn't matter. As long as temperatures are the same, we assume that saturated liquid and compressed liquid, there is no difference. So U is UF at the same temperature. H is HF at the same temperature. So that's how you evaluate a property of compressed liquid when pressure is low. Then the next question is, what about when pressure is high? How high? Equal to 2.5 megapascal or greater. Then we already saw the table. Table A5, compressed liquid table. So this is a summary how to evaluate a property of phase change material. Of course, these table numbers 2, 3, 4, 5, they are the tables for water. So if you have a phase change material other than water, you need to go to their own tables. Okay, so if you go to the back of your textbook, you will see 96 pages of tables. So some are for water, some are for the other materials. Okay, we have 10 minutes, so let's see how we can evaluate a property. So we are going to practice how to evaluate property together. So this is number one, how to make property diagrams to determine the phase change process. Once you determine the phase change process, these are how we evaluate its property. Just to motivate you, 40% of the first exam is only about how to evaluate a property. 40%. Then let's see how we can practice. this is a problem that we are going to study together. And this is the problem that you will see in your first exam. Of course, you will have different numbers. But this is how we practice, the evaluating a problem. So let me explain, how this table works. Each row is an independent problem. So how many problems in this table? There are 5 problems. So what you are going to do is, let's look at the first problem. In the first problem, we know 2 property values, and we are going to evaluate all the others. So in the first problem, we know pressure, that's 200 kilopascal. We know quality X, that is 0.7. So you are going to evaluate its temperature, specific enthalpy, and the phase change process. So that completes the first problem. In the second problem, we know temperature and specific enthalpy. So by using these 2 values, you are going to determine the phase change process, and you are going to evaluate its pressure, its quality X, and etc. So there are, you can see, 5 problems, and you will see a similar table in your first exam. That's going to be 40%. Okay? 40 not enough, but it's a free credit, already 40%. And there will be a problem from the pressure in chapter 1, as I told you already. That's 20%. So 20% from the pressure in chapter 1, 40% looks like this table. So already 60%. Then what is the remaining, the 40%? 20% should be from chapter 2 and what we studied. Kinetic energy change, potential energy change. You are pretty, familiar with them. So 20% from chapter 2 is free. 40% you already know. 20% from pressure in chapter 1. So you already have information about 80% of the first exam. Isn't that nice? Then what is the remaining 20%? From chapter 3. So if you just, stick to, what we covered in the classroom, you already, you're guaranteed to get 80% of your first exam. So what makes who gets A, B, C, D, F depends on the remaining 20%. No? Okay. Actually, I'm going to talk about, the 20% later. So you will get 100% about your, the first exam. So it depends on how much you practice, how much you put your effort. If you make a mistake here, then that's how, who gets 100%, who gets 80%, who gets 60%. There's no surprise in my exam. I'm going to disclose everything about the first exam. So you just need to, the practice. You just need to put your effort. Okay? Isn't it, the easy class? No? Okay. So we have about 5 minutes. So let's practice maybe the first 2. Okay? So we have 200 kilopascal and 0.7 is the quality X. So what we need to do first, we need to evaluate the phase change process. And we need to determine the phase change process. But wait, before we make these property diagrams, if you come here in the second, the second page, we learned a new parameter that is quality X. That's a ratio between saturated liquid and saturated vapor. If it is between 0 and 1, you have a phase change process number 3, saturated mixture. If X is 0 saturated liquid, X1 saturated vapor, there is no X, there is no X. So we can determine the phase change process by X. Then what is the X value? 0.7. So if you have 0.7, you can determine the phase change process. X between 0 and 1. There is only one phase change process, saturated mixture. So from that, you can say, oh, this one is phase change process number 3, saturated mixture. Then you can go back here. So we know it is saturated mixture. We have a pressure. So we are going to end up making this TV, TU, TH diagram. And we don't have to because we already know our system exists as saturated mixture. Then what is the pressure and what is the temperature of this saturated mixture? T set. Since it is a saturated mixture, which means it is presently undergoing phase change, what is the temperature? Saturation temperature. So we just need to find the saturation temperature at 200 kilopascal. Saturation temperature at 200 kilopascal. So this is phase change process number 3. At 200 kilopascal on this table A3 pressure table, and there is a 200. Wait, it's 2, but the unit is bar. So 2 bar is 200 kilopascal. What is the saturation temperature? 120.2. So you can write 120.2. Yes. Yes. Not all of them. There are 96 pages. So some of them. But if you need, let's say, 3 tables, I may give you 5 tables. If I give you the exact table, then that's not fair, right? I may give you more tables than you need. So you need to select. Okay, this is the table I'm going to use. Because I need to evaluate whether you can, find the right table or not, right? So there is a 200 kilopascal, T set is 120.2. Then do you remember how to determine H? If you don't, go back to this summary slide, and we know it is saturated mixture where is linear interpolation. H is HF plus quality X, HG minus HF. So let me write this equation here. Oh, different color. H is HF plus quality X, HG minus HF. Then what is HF? At this pressure, here is HF, HG. So the numbers we are looking for is these two. HF, HG. So this one is 504.7. What is quality X? 0.7. What is HG? 2706.7. HF, 504.7. So if you do the calculation, you get H value. Approximately 2,000 something, right? Now, there's one thing that we need to, agree. So, this value, temperature, is directly from this table, right? 120.2. So, if you write, instead of 120.2, if you write 120.1, is this correct or not? Incorrect, because the value is not the one that you calculate directly from a table. So if you write the wrong number, even though it is close enough, this one is not correct, okay? but this one is what you calculate. So approximated value is okay. So if you need to calculate this value by an equation, if you get a close value, you will get full credit. However, this one, since this value is not after calculation directly from a table, if you to get a closed value, that is incorrect in your exam. That's how I'm going to grade. So this is just one example, and we will solve the rest of the, we will complete the rest of the table next Tuesday. Okay. Just for your information, we can complete this table next Tuesday, and we will study one more thing, that is ideal gas equation of a state. That will be enough for our first exam. So our first exam would be the week after, so the following Tuesday. Okay. If you have a conflict, just let me know in advance. Okay. Thank you.